This test method covers on how to determine the weight per meter cube of a freshly mixed batch of concrete so that we can get the data needed like the yield of cement, cement content, and the air content of the concrete. The information obtained through this test can also be used to determine the yield and the relative yield, which helps you verify that you are getting the volume of concrete that you ordered and paid for. You can also use this data to calculate the air content of the mix. The downside of not doing this test will result on us not knowing if the batch will be replaced because it didn't achieve the standard of the mixture. And replacing a batch of freshly mixed concrete will cost a lot of money and a setback on time. The importance of this process is so that we can get the necessary data to know if the batch of freshly mixed concrete is up to standard and can be used in construction, so that potential accident can be prevented.
The test will be conducted as based on the following standards. Standard number ASTM-C 13877 ASTM 121. And as for equipment and materials, the balance to be used in measuring the weight of the mixture. We will need the balance or scale accurate to within 1 pounds or 45 grams or 0.3% of the expected test range of whichever is greater. The tamping rod. The tamping rod to be used in reducing air bubbles within the slump. Depending on the slump, we may need a tamping rod with a diameter of 5/8 inch and with a length at least 4 inches greater than the depth of the measure to be used, but not more than 24 in long. And with at least one end of the rod, the tamping end shall be rounded to a hemispherical tip of the same diameter. For the measure will be used to contain the mixture. The dimensions of the measure to be used will depend upon the maximum aggregate size in the concrete mixture. However, in no case shall the measure be smaller than 0.2 feet cube. The measure must be made out of steel or any other suitable metal and must be calibrated in accordance to ASTM C29. Strike-off plate must be 1/4 inch in thickness if made of metal and 1/2 inch if it is made of glass or acrylic, and its side must be at least 2 inches or 50 millimeters greater than the diameter of the measure. And lastly, for the calibration equipment or calibrated scale will be used in observing the accuracy and exactness of the weights measured.
To perform this test, dampen the inside of the container. Find the mass of the empty container. Place the container on a flat, level. Fill the container with 3 layers of concrete of an equal volume and rod each layer with 25 blows. Since the slump is greater than 3 inches, then the method of consolidation is by rodding. When rodding the next 2 layers, penetrate the layer below them by about 1 inch. After each layer is rodded, tap the sides of the container 10 to 15 times with a rubber mallet. But in case your slump is 3 inches below, you can use method of vibration. The final layer must not be overfilled. Finally, strike off the top surface of the plate. Clean the excess concrete off the sides of the container and then weigh the container full of concrete. You can calculate the unit weight, theoretical density, yield, relative yield, cement content, and gravimetric air content.
Now let's go over to calculations. So first, let's define what is unit weight. Unit weight is the weight of the concrete per a given unit volume. Now, to report the density or unit weight, we want to report it to the nearest 0.1 pounds per cubic foot. We do this by using the following equation. W equals M subscript C minus M subscript M divided by V subscript M, where W is the density or unit weight of the concrete in pounds per cubic foot. M subscript C is the mass of the measure filled with the concrete in pounds. M subscript M is the mass of the empty measure in pounds, and V subscript M is the volume of the measure in cubic feet. Let's go ahead and do this in our observed data. The mass of the measure with the concrete on it is 96.7 pounds. The mass of our measure or the mass of empty bucket is 15.4 pounds. And the volume of our measure is 0.5650 cubic feet. So here, what we want to do is take the mass of our measure filled with concrete. This is 96.7 pounds, and subtract from it the mass of the empty measure or M subscript M, which is 15.4 pounds. This is going to leave us with the weight of just the concrete. We now want to divide its difference by 0.5650 cubic feet, and rounding to the nearest tenths of a pound, we should come up with an answer of 143.9 pounds per cubic foot for this concrete. So let's go ahead and do some yield calculations based on the unit weight that we just achieved. So for our observed data, we have just determined our unit weight, which was 143.9 pounds per cubic foot, and we've handed a batch ticket that says 27,300 pounds of total material in the truck. And we know that the concrete has been designed for is 7 cubic yards. We now have to calculate our yield per cubic foot and yield per batch in cubic yards. Once we achieve these numbers, we're going to go ahead and calculate the relative yield for each conditions. Now, the first calculations we're going to do is the yield per batch in cubic feet, and this is a very straightforward calculation. It is W1, the mass of all materials batched, which we've already determined to be 27,300 pounds, and we want to divide it by the density, which we determined to be 143.9 pounds per cubic foot. So therefore, we take the 27,300 pounds, we divide that by the 143.9 pounds per cubic foot. And again, basic math, pounds will eliminate pounds, leaving us only with the cubic feet, and therefore, we have the 189.7 cubic feet in this truck. Our next calculation is yield per batch in cubic yards. This is similar to yield per batch in cubic feet, except here, we are going to take our density and multiply it by 27, the amount of cubic feet in a cubic yard. So if we take the mass of all materials batched, 27,300, and divided by 143.9 pounds per cubic foot times 27, we end up with a yield of 7.03 cubic yards. Now we can move on to the relative yields. Relative yield is the ratio of actual volume of concrete produced to the volume of concrete as it was designed. So to determine relative yield, all we have to do is we take the yield, which is the amount of concrete that was actually produced in batch, and we divide it by Y subscript D, which is the amount of concrete for which the batch was designed. So if we're to do the relative yield per batch per cubic yards, it would simply take the 7.03 cubic feet, the amount of concrete that was produced in the batch, and divided by 7 cubic yards for which the batch was designed, resulting to a relative yield of 1.00. So a question that frequently comes up is what is wrong with overyielding? You wind up with more concrete and it's not a good thing. Well, let's take a look at that by calculating the actual cement content. Again, in this particular case, we designed for 7 cubic yards, but we over-yielded to 7.03 cubic yards. So the calculation here is N equals to N subscript T divided by Y subscript D, where N is the actual cement content in pounds per cubic yard. N subscript T is the total mass of the cement batched in pounds. And Y is again the yield or the volume of concrete which was produced in cubic yards. Sticking with our case, we designed for 7 cubic yards and we yielded 7.03 cubic yards of concrete. And on this data, we have this concrete of 6.5 sack mix, meaning that we wanted 611 pounds of cement in each cubic yard. And our N subscript T will be coming from the 611 pounds of cement that we want in each cubic yard multiplied by the designed 7 cubic yards. So if we return to our equation, here we have 4,277 pounds of cement was batched out, and we're going to divide this by the 7.03 cubic yards of material that we yielded. And it's going to give us 608 pounds of cement per cubic yard, which is 3 pounds per cubic yard less than we actually designed for. So where did the cement go? Don't forget that concrete is placed into geometric shapes of specific volume. The moment that volume is filled with track, drives away, and in that track is going to be that additional concrete as well as the cement which was supposed to be in your forms. Now, the last calculation that you may be asked to do is to calculate the air content using the gravimetric method. What we want to do is take T, which is the theoretical density, minus the actual density divided by the theoretical density times 100%. And the quick note, the theoretical density is the density of the concrete computed on air-free basis in pounds per cubic foot. The theoretical density is determined using the total mass of all materials batched, W1, divided by the absolute volume of concrete. Here we have 27,300 pounds, divided by 183.84 cubic feet equals the theoretical weight of 148.5 pounds per cubic feet. So here, if we have the computed theoretical weight of 148.5 pounds per cubic foot, we want to subtract from that is the actual unit weight of 143.9 pounds per cubic foot. Divide this number by the theoretical unit weight 148.5 pounds per cubic foot times 100% gives us an air content gravimetric of 3.1%. And this is going to conclude the calculation of ASTM C138 standard test. Track type. Now, to analyze the computed values. Unit weight is determined using a 0.5650 cubic foot container. The weighted empty container is subtracted to the weight of the measure filled with concrete. The resulting value is an 81.3 pound difference, which will be known as the weight of concrete. That weight is divided by the volume that shows the density of 143.9 pounds per cubic foot. Yield is determined as batch weight divided by density. This is converted to relative yield, which is the volume of the concrete received divided by the volume of the producer intended to provide. Since the relative yield is 1.00, then it's exactly the same and expressed as cubic feet per cubic yard. Therefore, we get the volume of the producer said he shipped. If the relative yield is more than 1.00, it means you have received more, which usually means the air content is higher than specified. In the computed air content value in the previous calculation, there is a 3.1% change in air content, proving if relative yield is lower, the air content is low.
As a conclusion, the density or unit weight is a critical parameter for determining the consistency of freshly mixed concrete. Following the establishment of a concrete mix design, a change in the density of the concrete would signify a change in one or more of the other concrete performance criteria. A lower density can indicate lower specific gravity of the cement or aggregate than expected, higher air content, higher percentage of water, change in the ingredient proportions, or if there's less cement in the mix. A higher density on the other hand would mean the polar opposite of the aforementioned characteristics. On the other hand, yield of the concrete as delivered at a job site can be checked by the contractor by regular measurement of unit weight. If this varies more than 2%, an investigation should be made into such factors as air content, aggregate weight, or batch weights. When the unit weight varies considerably, it will often be found that yield is varying, as well as the other concrete properties. If the proper volume of concrete was delivered to the job site, and if suitable allowances have been made for unavoidable yield losses in placement, and a sizable shortage of concrete still turns up, the contractor can be certain that he has his own practices to blame. Or, if it develops that the job is completed before a good deal of the anticipated concrete is delivered, the contractor cannot rest easy. There's always the knowledge that overyield means lowered strengths. Obviously, it is of the greatest importance to maintain yield correctly, as it can also be used to determine the air content of concrete. As long as the theoretical density of the concrete computed on an air-free basis is known, all parties benefit when yield is kept in bounds, and all stand to lose when it is allowed to vary substantially.